Thank you for thanks for waiting. Thank you for staying up this late or waking up this early. I'm Ines Corte. I'm from Argentina, and I'll just get right into it. Okay. So, as an outline of the talk, I'll be talking a little bit about skyrmions and specifically what I mean by quantum skyrmions. I'll be showing you some of our preliminary results. For instance, I'll be showing you the magnetization and specifically the entanglement entropy. And then I'll just try to, if I can, I'll try to mention shortly some of our partial conclusions and future ideas, more things we have to work on. So, in a nutshell, magnetic skyrmions are 3D magnetic textures that are characterized by this quantity here that's called the scalar chirality, which is a discrete version of the topological charge. And what I'm showing you here is the arrangement of the magnetic moments of in the lattice, for instance. And the colors here are just a visual aid. They are just trying to show, to signify that they're just trying to show the different angles of the magnetic moments, the magnetic moments formed with the Z axis. In these pictures, blue would mean that the magnetic moments are pointing downwards, red would mean that they are pointing upwards, and the colors in between of them means that they are tilted in some angle that it's not in between of those, okay? And when this quantity I was telling you about is equal to plus or minus 1, we can say that we have a skyrmion. And as I mentioned, sorry, I'm a little bit nervous. As I mentioned, I'm saying that these objects are topological, and by that I'm trying to say that you could map the spins from the left into a sphere on the right, and you can map them considering the different angles that the different directions of in which the magnetic moments are pointing. If you map all the I'm going to say spins, sorry, all the spins pointing downwards to the South Pole and the ones that are pointing upwards to the North Pole, and all the others in between into the other corresponding angles. If you can do that, then you can say you have an skyrmion. And there are different Hamiltonians that you could use, but for instance, the typical Hamiltonian used to study these systems is the one I'm showing you below. And this involves the presence of a simultaneously of exchange interactions and this interaction called the Alechinsky-Marisha, in which the vector D has to have some on-plane component. And the classical skyrmions in this case would be stabilized with some value of with some non-zero magnetic field. Okay, this is the case for ferromagnetic skyrmions, but you could also have antiferromagnetic skyrmions. I'm going to talk specifically about the antiferromagnetic skyrmions that appear on a triangular lattice, because that's the lattice I'm going to be studying later on. And what Rosales and company found on their paper of 2015 is that you could obtain a magnetization profile as the one shown in the left, but that could be interpreted as 3 different ferromagnetic lattices interpenetrated. There are the 3 pictures I'm showing you on the right. And these systems are of interest specifically because they have some potential applications as information carriers, because they have some specific qualities that make them really suitable candidate for those systems. So the thing is that these skyrmions have been experimentally measured, and they have been measured, and the sorry, they have been measured, and skyrmions of sizes similar to the interatomic distance have been measured as well, and in taking that into consideration, it makes it relevant to consider the quantum properties of the skyrmions. There have been some recent papers that have been studying analogous quantum ferromagnetic skyrmions, and they have obtained pictures from such as the ones I'm showing you below. These ones are from the magnetization profiles of this system in a triangular lattice, and we were trying to know if there could be as well an analogous antiferromagnetic skyrmion. And so to do that, we need different ingredients to actually reach it, or at least try to reach to this conclusion. We have to define the Hamiltonian we were going to use, which is one which is pretty similar to the one I was showing you in the first slide. In this case, we're considering the exchange interaction to be antiferromagnetic interactions, and so the parameter J is positive. Then the system specifically we're trying to study is a system of 12 times 12 system of 12 times 12 spins, and we're trying to study them on a triangular lattice. And to study the quantum phases, what we did was to obtain the ground states of the system using the density matrix renormalization group. So I'm just going to show you briefly the results. Here, just as a comparison, I'm showing you the magnetization obtained in the antiferromagnetic system on the top and the ferromagnetic system of the same size on the bottom. Both of them show that the magnetization after a certain value of B, it kind of reaches its maximum value and it stays that way, which is what we expected, because after a critical value of B, the system reaches a field polarized phase. But as you can see, both of the magnetization profiles are quite different. Sorry, the magnetization in both systems is different. And about the magnetization profiles, as you can see, we obtained some magnetization profiles which are similar to the ones I was showing you before on the antiferromagnetic skyrmion lattice. Okay. So now about the chirality, as I was saying a little bit earlier, the chirality was the quantity that signaled the emergence of a skyrmion. And in this case, since we're trying to consider a quantum quantum analogous system, we are studying a quantum version of that chirality, which instead of having the triple product of the magnetic moments, what we have is the expectation value of the triple product of the spin operators. And the results are the ones I'm showing you in these two pictures below. The picture from the left shows the chirality of the total lattice, which is labeled with blue triangles, and in the sublattices, and the mean value in the sublattices, which is signaled with the purple triangles. And we can see here that there is a specific region in which the chirality of the entire lattice is obviously non-zero, which we could say it's signaling some sort of phase that could be related to skyrmions. And now, I mean, oh, sorry, 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 I'm really nervous. I'm trying to.
No worries. Take your time. Take a breath.
Sorry. Okay. So up until now, we've shown our results, which have some similarities with the classical results, but we would like to know if our results are truly quantum. And by that, what I mean is that if our quantum spaces have actually quantum entanglement, which are quantum correlations and do not have a quantum analog. And so if we can prove that there's entanglement, we could say that these results are actually quantum states, are truly quantum states. There are different ways of measuring the entanglement, and one of the entanglement measurements that could be used is the von Neumann entropy or entanglement entropy, which is given by the expression here below. Rho sub A is the reduced density matrix of the subsystem A, and in order to obtain the entanglement entropy, what you do is to take your whole system and just divide it into two chunks, into two subsystems, which I will be labeling as A and B. In our specific case, there's a thing I didn't mention up until now because I didn't think it would be of it would be it would matter up until now, is that what we were studying is a 2D lattice, but in order to use the density matrix for normalization group, what we had to do is to map this 2D system into a 1D system. And so here for the entanglement entropy, what we will be considering always our B partitions will always be just two contiguous blocks as the ones I'm showing you here below in the right. And now, finally, what we're trying to do here is to compare the entanglement entropy with the chirality, because once again, it was the quantity that signaled if there was something skyrmion-like or not. And we're trying to see, on the one hand, if there's actually entanglement in a specific region or not, and on the other hand, if the entanglement entropy has some specific behavior that could be related to the behavior that has another quantity. And in this case, for instance, we're trying to see if it has some similar behavior to the one the chirality has. And so in the first picture, we are showing the maximum of the entanglement entropy for each value of the magnetic field, and we compare it to the total chirality of the entire lattice. Then in the second picture, we are comparing the mean value of the entanglement entropy and the chirality. And in the third picture, what we're trying to compare is the entanglement entropy in between two halves of the system. I mean, with half chain entanglement entropy, what I mean is that we took our whole chain, we divided into two, we cut it into two parts, and both parts are equally sized. And so we're comparing the entanglement entropy of these two equally sized parts and the chirality of the entire lattice. And I'm going to focus specifically on the third picture. What we saw is that both the entanglement entropy and the chirality have a significant change in the exact same values of B. In the case of the entanglement entropy, it has a jump, and in the case of the chirality, it starts to be significantly non-zero. And moreover, as you can see here, with the green dots, in the region in between 0 and about between 0 and 1.6 of the magnetic field, the values of the entanglement entropy are notably different with respect to the ones here in our what I will call our region of interest. And so by this, what I'm trying to say is that we are having non-zero entanglement in a region we wanted to have non-zero entanglement, and also the behavior of the entanglement entropy has similar changes in the same values of V as the chirality has. And so we could say we could actually maybe use the entanglement entropy to signal the different phases that appear in our system. So, okay, finally, I'm going to jump to the conclusions. So, long story short, we have seen different results are maybe, well, at least for us, our results are signaling the appearance of some quantum phases that could be quantum analogous to the antiferromagnetic skyrmions. We've seen there's entanglement present, and so we could say that our states are actually and truly quantum states. And of course, there are more things to do. For instance, we could we would have to make some finite size scaling of our system. I mean, by that I mean trying to reach into larger system sizes, and of course change the values of change some of the parameters of the DMRG. For instance, I don't know, maybe adding some noise term to just in order to see that if our ground states, the ground states we obtain are actually ground states, or maybe, I mean, they could be a local minimum instead of a global minimum. And that's about it. I'm leaving you here some of the references of the works I was mentioning during the talk. And once again, thanks for listening.
Thank you, Ines, for your talk. Okay, so entering the Q&A session, does anyone have any question for Ines? Cody has a question.
Yes. Hi, Ines. Thanks for this interesting work. I'm curious, you described entanglement entropy versus chirality, and I didn't exactly understand the two scales that you had going there. Specifically, you're describing like a non-integer chirality. How do you maybe describe that? Can you comment on that?
Yeah, the comment would be that apparently in these works, for instance, the ones I'm citing here, well, no, not on both of them, in this one specifically, they've obtained a chirality of 1/2 on the region that it was supposed to have a ferromagnetic skyrmions. So I'd say maybe it's a quantum effect on the value of the chirality. What I think is important here is that the chirality is basically non-zero. It has a significant non-zero value. And why it isn't about that, I wouldn't know why exactly, but all I'm saying is that there have been other works that also show these values of I don't know, for instance, 1/2 of chirality instead of 1 or -1.
Okay. And then just to be clear, sorry, what are the two scales? You have horizontal and vertical.
Yeah, the horizontal scale is the magnetic field, but I'm dividing the magnetic field with the parameter d, that is the strength of the Dialshinsky-Morisha interaction. And the scale, the y-axis, it would be, actually it's a mixed scale because it has both the chirality and the entanglement entropy. All I was trying to show here is that the behavior of both quantities on the same graph, just to try to find out if there's actually some similar behavior in both of them, if they change in the same values or near the same values of B or what.
Okay, thank you. Yeah, very interesting. I appreciate it.
Thank you.
Okay. I don't see any further questions. Okay, thank you, Ines, again for your